Hey everyone, this video will be on the topic of entropy. Entropy, denoted by the letter S, is another thermodynamic quantity that measures the disorder of a system. When a system that consists of particles or molecules have a high entropy, it is described as being more disordered or being more disorganized and more chaotic. Vice versa, when a system has a lower entropy, it is described as less disordered or more organized and less chaotic. A simple diagrammatic comparison between a low entropy system and a high entropy one can be simply seen by different states of matter. In solids, the particles are compact and well arranged. They have very minimal movement and motion. Therefore, they have a low degree of disorder because their position and movement are much more predictable. In a high entropy system, molecules and particles will be moving in all sorts of directions and with very high relative motion. So their position and motion in a given instance will be much more unpredictable. So hence why it is described as more chaotic, more disordered, and therefore higher entropy. The unit of entropy is usually given in joules per Kelvin, which is the SI unit for temperature, per mole, referring to a specific quantity that is 1 mole of a particular substance. Let's compare enthalpy, H, versus entropy, S. Enthalpy and entropy are both thermodynamic quantities, meaning they describe the physical properties, specifically the macroscopic properties of a system. Macroscopic properties are referring to the bulk properties of a system, what you can see as a whole, such as energy, temperature, pressure, or volume, rather than the individual behavior of the atoms and molecules. For example, enthalpy represents the total heat energy of the system. So when we refer to enthalpy change, that refers to the energy change that's associated of a chemical reaction. The energy is one of the physical properties of the chemical system. Enthalpy is measured usually in kilojoules per mole or joules per mole. And by way of review, in the video on enthalpy, we talked about that the enthalpy is equal to the internal energy of the chemical system plus the pressure multiplied by the volume. These are the three physical properties that will contribute to the enthalpy of a system. In contrast, entropy measures the macroscopic degree of particle or molecular disorder. So looking at the system as a whole, what is the net effect of the individual atoms and molecules and how they move around? How do they contribute to how disorganized or how chaotic the system looks? So this is again describing the macroscopic property of a system. In contrast to kilojoules per mole, the unit for entropy is usually measured in joules per mole and also per Kelvin. The per Kelvin here is a key unit that distinguishes entropy from enthalpy. The concept of entropy is explored in the second law of thermodynamics, which states that for any processes, the total entropy of the universe, so everything included, must increase no matter what the process is. Mathematically, this can be put into a simple equation, that is the change in entropy of the universe, which is equivalent to the addition of the entropy change of the system, and in the context of chemistry, we usually refer to the chemical reaction when we say the entropy of the system, added on to the entropy change of the surrounding. So that is everything else in the universe that is surrounding the chemical reaction itself. So when you add the two entropy changes of the chemical reaction, which is a system, and its surrounding, that is not related to the chemical reaction, should always increase. That is, the entropy change of the universe must always be positive. This is the second law of thermodynamics. A simple day-to-day example that showcases the second law of thermodynamics is the operation of a refrigerator. A refrigerator aims to extract heat from inside the refrigerator, which we refer to as the system or the chemical system, because that's where the actual operation of the refrigerator is actually taking place. And it aims to defer this heat into the outside part of the refrigerator. So because the temperature or the total energy inside the refrigerator, that is including all the food and drinks you've stored inside it, has decreased, you expect the particles and molecules that make up these items to also become more settled move around less, and therefore as an entire system, they become less disordered. So they become more compact, more organized, and their position and motion become more predictable. Now, as the heat is extracted and transferred into the surrounding, the air molecules or anything really surrounding the refrigerator will then absorb this heat and therefore will become more disordered. In the second law of thermodynamics, we know that the change in entropy of the entire system, that is the refrigerator, which is the system, plus the surrounding air, must be greater than zero. So even if the entropy change of the refrigerator itself is negative, that is, it decreases, the entropy change of the surrounding must be positive and specifically must be greater than the magnitude of entropy change of the system itself, such that when you add the positive entropy change of the surrounding to the negative change of the entropy of the system, you should still get a positive change of the entire universe, such that it will be consistent with the second law of thermodynamics. With reference to a chemical process or reaction, the entropy change can be easily calculated by finding the difference between the sum of entropy of all the products and the sum of entropy of all the reactants in the chemical reaction. We'll apply this formula to a few examples at the end of the video. As I mentioned in the beginning, entropy of a system is affected by the state of matter of the substances that occupy that particular system. Solids have the lowest entropy, whereas gases have the highest entropy. And this is all to do with the molecular motion. In solids, the particles, atoms, and molecules are more compact. They are brought together by intermolecular forces, therefore their motion is more restricted. So their position is more predictable, and therefore we say they have a low disorder or low entropy. As solids transition to liquids, more energy is absorbed, and as a result, these particles and molecules will start to move around a lot more. Their motion and position become more unpredictable, and therefore they become more disordered. So the entropy of the system increases. The same thing will occur when liquid evaporates to become a gas. So gases have the high entropy out of all three states. So the process of melting and evaporation will both increase the entropy, whereas the process of freezing and condensation, going backwards from gas to liquid to solid, will decrease the entropy. The variation in entropy according to the state of matter has a significant impact on the entropy change of chemical reactions. For chemical reactions that tend to produce a gas, for example, the decomposition of calcium carbonate solid to form calcium oxide solid and carbon dioxide gas, entails an increasing entropy because the reactant, calcium carbonate, is in solid state, and after the chemical reaction, it produces calcium oxide, which is also solid, so it will have relatively low entropy, but the production of carbon dioxide gas, due to its gaseous state, will increase the entropy of the system, such that the entropy of the products combined should be higher than the entropy of the original system composed of only solid calcium carbonates. This combustion reaction of octane, which is C8H18, a liquid fuel at room temperature and pressure, is also an example where the production of gases usually increases the entropy of the chemical system. In this chemical reaction, we start off with liquid octane and also 25 oxygen molecules, which again, being a gas, will significantly increase the entropy of the chemical system in the beginning before the reaction has taken place. However, the combustion reaction produces 18 molecules of water, liquid, and 16 molecules of CO2 gas. Both the liquid water and the gaseous CO2 molecules in combination will have a higher degree of disorder and entropy compared to the reactants combined. This is particularly because most of the atoms, that is the carbons and hydrogens, are concentrated and found in the liquid state of octane, which has a relatively low entropy compared to the sum of all of these liquid and gas molecules in the products. So this reaction highlights that even though you may start off with a gas reactant, it is important to compare the sum of entropy of all of the reactants with that of the products in order to determine a more accurate picture on whether the entropy of the reaction increases or decreases. In general, for combustion reactions, the entropy generally increases. In addition to the state of matter, the complexity of a molecule or compound also affects its entropy and also the overall entropy of the chemical system. The general rule of thumb is the more complex molecules are, they will have greater degree of disorder and entropy. And this is because more complex molecules usually will contain more atoms, and with more atoms, you will have more bonds between the atoms. And this increase in atoms and bonds will allow for more possible arrangement of the atoms and also rotational motion and translational motion of the atoms around the bonds. Methane and ethane are two simple examples of hydrocarbon molecules consisting of carbons and hydrogen only. Ethane has a numerical entropy value of 230 compared to that of methane, which is slightly lower of 186. Both of these molecules are gases under room temperature and pressure, but the reason why ethane has a higher entropy is because of the fact that it contains more carbon and hydrogen molecules. In methane, the total possible motion of the hydrogen atoms around the carbon is limited by the fact that there are only 4 bonds. However, in ethane, the greater complexity and increased number of atoms means that there are more bonds for translational motion between the atoms to occur. That is, the atoms can either move towards each other or away from each other at any given time in a random fashion. And in addition, there can be rotation around a bond to further add to the number of possible configurations or position of the atoms in the molecule at a given instance. So in summary, the more atoms and more bonds there are in the molecule, this generally increases the possible arrangement that they can have, and this will lead to a higher disorder and therefore entropy of the system containing these molecules. In thermodynamics, although both increase and decrease in entropy are possible with chemical processes and reactions, an increase in entropy is generally regarded as favorable. What this means is that molecules and particles prefer to increase in entropy and become more disordered via a process than the reverse reaction where they decrease in entropy. Another way to think about this is when a process would undergo an increase in entropy and become more disordered, it will be more likely to occur spontaneously, that is, occur without any further input of energy from the outside of the system, so from the surrounding. A good analogy to remember that an increase in entropy is favorable and a decrease in entropy is not favorable is relate to the tidiness of your room. Imagine that the tidiness of the room, or how messy it is described as the entropy. When your room is very tidy and organized, the items and things are put in the exact spot they belong to. This is described as low entropy, so low degree of disorder. When it becomes more messy and more untidy and things are misplaced all over the place, that the entropy of the room is described as high, so high degree of disorder. Now think about this. Is it easier for you to maintain your room in a tidy state or when it becomes more messy, when things are lying around all over the place? Hopefully your answer would be the latter. It will take you much more effort to tidy up your room regularly to maintain this in a low entropy states. In contrast, over time, if you don't put in the work and effort to return things back to where they were and to tidy your room on a regular basis, your room would easily become the picture shown on the right here, where it has a high entropy and high degree of disorder. The same principle applies to chemical reactions, particles, and molecules. Particles and molecules prefer to become more disordered. It is more favorable for them to do so and have an increase in entropy than the other way around, where they become less disordered and have a lower entropy. So remember, when it comes to chemical reactions, an increase in entropy is always preferred and favorable for particles and molecules. Let's walk through 2 examples on how we can calculate the entropy change of a chemical process. Calculate the standard change in entropy. So the word standard here refers to standard conditions. So that is room temperature and atmospheric pressure. When 50 milliliters of water evaporates to form steam. So this is water liquid transitioning to form water gas. So this is a physical process. Standard change in entropy is often represented by S naught. The naught here refers to the values measured under standard conditions. So we can calculate the standard change in entropy by taking the entropy of the product, which is the gaseous form of water, so gas, minus the entropy of the water in liquid state. So this will be 188.7 kilojoules per Kelvin per mole minus 69.94 for liquid water. This gives a value of 118.76, and we'll round this to 4 significant figures, 118.8 joules per Kelvin per mole of water. Calculate the standard molar change in entropy for the complete combustion of octane. So this refers to a chemical reaction. Before we can calculate the entropy change, we need to first write a balanced chemical equation. C8H18, this is liquid in standard states, plus oxygen gas produces carbon dioxide gas plus water liquid. So these are the products of complete combustion. We'll put an 8 in front of the carbon dioxide to balance the carbons. We'll put a 9 in front of the water to balance the hydrogens. And now on the right hand side, I have 17 oxygen atoms. So I can easily put 17 over 2 in front of the O2 gas to balance the number of oxygen atoms. Balancing the equation before the calculation step is important because the stoichiometric ratio will affect the entropy of each of the chemicals. This is because the entropy value in the table is given as per mole. So it's based on how many of the reactants are consumed and how many of the products are actually produced. So again, the change in entropy under standard state is equal to the sum of entropy of the products, again under standard states, minus the sum of entropy of the reactants under standard conditions. So the products are CO2 and water. CO2 is 213.7. Now this is per mole. We need to multiply this by 8, which is the molar ratio in front of CO2, right? So this is because for every 1 mole of octane used, you'll produce 8 moles of CO2. So you need to times this value by 8 to reflect that number. And we'll add this to the entropy of water liquid, which is 69.94. And we again have to multiply this by the number in front of the water liquid, which is 9. So this is the sum of entropy of the products. And we're going to subtract this by the entropy of the reactants. So first we'll start with octane liquid, 329.3, and there's just one of them, so it just times by 1. And notice how even though octane is a liquid, it actually has the highest entropy out of all the chemicals. So this is to show that the state of matter is not the only factor that can affect the entropy of a chemical. The complexity of the molecule here also contributes to that. Octane, being the most complex molecule in this example, consisting of the most number of atoms, has the highest entropy despite the fact that it's only a liquid. So this is the reason why octane has the highest entropy value compared to even the gaseous species like CO2 and water. Now, we need to add the entropy of the octane to the entropy of O2 gas, which is 205.0, and we'll have to multiply this by 17 over 2 to reflect the stoichiometric ratio. This gives an entropy value of 267.26, and I'll round this to, again, 4 significant figures, so 267.3, and the unit here will be joules per Kelvin, and this will be per mole of octane, because we've calculated this based on 1 mole of octane combusted, because we only times this by 1. And so this is the molar standard change in entropy of combustion of octane. Hey everyone, if you found this video helpful, smash that like button and don't forget to subscribe. Want even more? Become a Patreon member for early access to videos, exclusive Discord discussions about questions on chemistry and physics, and live preparation sessions for your exams. Don't forget to head over to our website for topic tests and practice exams to further improve your understanding and learning.